All right, so officially, good morning again. Welcome to the webinar. Today's topic is battery testing in the production line, do's and don'ts, where we talk about things that you should do and, of course, things that you should better avoid in order to achieve accurate, correct measurement results for battery testing, specifically in the production line. Main presenter today will be Roy Harley, Head of Product Management here at HIOKI Europe. Starting that, a little bit of introduction, what we will do. So in this webinar, it will take about 30 to 45 minutes. All of you as participants are muted, but we invite you to please ask us questions. This is a good opportunity. Please use for this the Q&A function that you see at the bottom in the task list of your Zoom screen. Please enter your questions in there whenever you feel like it. Through the presentation, after the presentation, we will answer those questions. The chat function is disabled, so please only use the Q&A function for this, for the question submission of the questions. We will also answer the questions by email, so you will get the answers for those questions that we cannot cover in our Q&A session, but also the questions that we already could answer after this. As well, with the link to the recording of this webinar. So this is recorded from the beginning to the end, so you could get the link and then recap the content that we are talking about in today's webinar. All right. From my side, very quickly, I would like to introduce HIOKI for those who are not so familiar with us. So in 1935, HIOKI started with the manufacturing of electrical indicating meters. That means next year we will fulfill our 19th anniversary, and throughout those 90 years, HIOKI has from the start been dealing with electrical measuring instruments, and ever since working in the same industry, in the same area. As of today, we have about 1,200 employees worldwide and a turnover of 250 million roundabout. What characterizes HIOKI very much is that we are an engineer-driven company. So the search for new technologies, new measurement methods, innovation in this field is really at the heart of the company. And another aspect that we would like to highlight, to date, still with this high volume and wide portfolio that we have, all of our instruments, let's say almost all of our instruments, 98% or so, roughly speaking, are made in Japan with Japanese precision. In Europe here, for you, very more interesting also, we are here established as HIOKI Europe since 2017 in Eschborn near Frankfurt. What we can tell about the portfolio of HIOKI. So we have those three categories that we can define, where we can define the portfolio of HIOKI, where we have altogether 250 main products at the moment. So starting from the left, you see the automatic test equipment is basically for production, for R&D as well, but mainly production-oriented quality assurance instruments for PCB and bare board testing. Then the pillar on the right, you see the field measuring instruments, which are basically handheld instruments for maintenance tasks in the field, from multimeters. We have earth testers, insulation testers, and so on. And the main part, the big block that you see in the center, is really the core of our business. We'd say the professional measuring instruments, which are benchtop measurement instruments made for accurate measurement that you can use in R&D, but also in quality assurance. And out of that, you see highlighted here or in bold some of those instruments which are relevant for battery industry, like battery testers, resistance meters, and so on. And this is the topic that we want to talk about today. To get a little bit of it in an overview, on the next slide, we see a timeline. So as early as 1986, HIOKI started with the first battery-related testing instrument, a milliohm tester that was launched only a year after Asahi Kasei started to produce lithium-ion battery cells on a wider scale. So we have a production-ready lithium-ion cells ready. So only 1 year later, HIOKI was there supporting with the measurement instruments for quality assurance. And over the years, as you can see, especially after the 2000s, with the new mobility, EVs speeding up, more and more innovations, more and more measurement solutions were provided by HIOKI, from data loggers, battery testers, resistance measurements. All these tools were developed and even sped up in development through the years. And based on this expertise, not only with the measurements, but also how to measure, strong and close communication with the industry. This is where we get the expertise from that we want to share a bit today, in about how to use those measurements in the right way, how to set it up in a way so that you can benefit from these instruments in the best way possible. Okay, so with this little introduction, also if you have questions about this, it's also very welcome. But we want to now go to the technical part, to the main part of presentation. I will hand over to Roy Harley, who will take on with the main topic from here on.
Okay, Oliver, thank you very much for the introduction. Before I'm going to dive into the technical part of the webinar, I'd like to explain why we decided to organize this webinar in the first place. At our office in Eschborn, in Germany, our customer support team frequently gets questions related to battery testing in the production line. Most of these questions are related to poor reproducibility of AC internal resistance measurement of the batteries. With the experience within HIOKI, supporting our customers in China, Korea, Japan, and Europe, we know what can go wrong with ACIR measurements, and we can give valuable advice on how to achieve accurate and reproducible measurement results. Let's go through the content of the webinar to give you an idea what we are going to cover. We will start with a short explanation of the principle of ACIR measurement, followed by measurement examples that show what can go wrong, what the reason might be, and what to do to solve the issue. After that, we will provide suggestions for troubleshooting in the production line, and we will close the webinar with a summary and a Q&A session. So, when we talk about internal resistance of a lithium-ion battery, it is known that the internal resistance is a reliable indicator of the quality of the battery. ACIR measurements are therefore popular test solutions in the production lines. Let's dive into the principle of ACIR measurement. The principle is quite simple. A stable AC signal, which is generated by the battery tester, is connected to the battery, and at the same time, the AC voltage over the battery is measured. And based on Ohm's law, we then easily can calculate the internal resistance of the battery. The measurement is done in accordance to the IEC 61960-3 standard that describes the way to measure. The standard specifies the frequency of the AC current signal must be 1 kHz. This is important because the internal resistance is frequency dependent, and when all tests are performed at the same frequency, it makes it possible to compare the results wherever the test took place. As the internal resistance of a lithium-ion battery is just a few milliohm or even less, it is necessary to use 4-wire measurement method. This method eliminates the influence of the connection resistance. The connection resistance consists of the wiring resistance and the probing resistance. And the connection resistance is very much higher than the internal resistance of the battery, and therefore you need to take the right consideration to make sure that you compensate for the wiring resistance in your measurement. The 4-wire measurement method works like this. The source signal, so the AC source current, is connected through these wires on the outside. So the measurement current is flowing through this circuit. At the time, the voltage of the battery is measured with this voltmeter, which is inside the battery tester. the internal resistance of this voltmeter is very high, meaning that in this circuit there is almost no current flowing. And because there is no current flowing, there is also no voltage drop over the connections, meaning that we can accurately measure the voltage over the battery. Now we know the basics of AC/IR measurement, we are going to look what can happen when you use a sensitive measuring instrument like a battery tester in a battery production line, and what you should do to ensure reliable and reproducible measurement results. Poor test results are related to mainly three categories: the wiring between the battery and the battery tester. Due to many motor inverter drives in the production line, electromagnetic interference is a common issue. Also, the effect of eddy current and the use of multiple testers at the same time can influence the test results. Probing is the second common cause for errors because of high connection resistance. The type of probing pins and the positioning of probing pins are very important and will be addressed in this webinar as well. Further, we will talk about the introduction of a multiplexer in the test circuit. Depending on the application and depending on the needs of the production line, it could be that you need a multiplexer in your measurement system. We will look into the pros and cons of that and also look at what you have to take in consideration if you decide to use a multiplexer. So, first we will start with the wiring. How can electromagnetic induction influence the test results? For starters, the battery is generating an AC current at 1 kHz. At low ranges, this measurement current is quite high. At the 3 milliohm range of the battery tester, the current that we are generating is around 1 amp. The current causes a magnetic flux, the blue arrows, that can influence the voltage sensing of the measurement instrument and it causes a problem with the accuracy of the measurement. Further, also other influences, like I already mentioned, inverters or any other electronic devices in the production line, can also have an effect, can also cause magnetic flux, which is picked up by the sensing circuit of the battery tester. An effective way to cancel the influence of electromagnetic induction is twisting wires. By twisting the high and low source wires, you bring them very closely together. In this drawing, the test current is flowing from left to right in the blue wire and returns in the orange wire in the opposite way. The current flowing through the blue wire is creating this magnetic flux, and by twisting the cables and returning them, the current flowing through the orange one is the same current as flowing to the blue one, and therefore this magnetic flux is cancelled out by twisting the wires. If we look then at the sense side, the sense side basically start with a magnetic flux which is generated either by the measurement current, if the wires are not twisted, or from inverter drives or other electronic equipment on the production line. So what happens when this magnetic flux is approached to the twisted wires? Well, basically, in the blue wire, it will result in a voltage, and induced voltage, which is shown with the blue arrows. But at the same time, if we are using a twisted pair, through the blue for the orange wire, the direction of the induced voltage is in the opposite direction, and therefore they are cancelling out each other. Maybe you think this is going a little bit fast, but I'm certain that with the following examples, we make things clear to you. For practical reasons, these tests are done on accurate milliohm resistors, but the effect will be the same on lithium-ion batteries. On the left-hand side, the battery tester is connected to a 1 milliohm resistor using untwisted wires. The test current is flowing through the source high wire, the yellow one, and back to the battery tester through the blue source low wire. In this way, we create basically an area in which there will be a magnetic field. And this magnetic field is picked up by the wires of the sense circuit. So the sense high, the red one, and the sense low, which is the black wire. So when this is picked up in the sense wires, it will induce a voltage which is interfering with the test. And that's why the accuracy of this one is quite poor. Well, we have seen in the previous slides that it is interesting to use twisted wires, and that it has an influence of cancelling out the influence of electromagnetic induction. And that's why we now, in the second, on the right hand side, you can see that the measurement is done with twisted wires. So on the left hand side, we have twisted the wires for the source, and on the right hand side, we have twisted the wires for the sense of the measurement. And immediately you see that the accuracy of the measurement is a lot better. And this is basically showing you that twisting the wire is a very effective way of cancelling out the electromagnetic induction. Then there is another issue which is related to magnetic induction, and that's the effect of eddy current. Eddy current, due to the magnetic flux generated by the measuring instrument, eddy current is flowing through metal plate surfaces that are near to the source wires. As a result of this, you see here this eddy current. Another magnetic flux is generated, so the left blue arrow here, and that is also picked up by the source or the sense wires of the measurement instrument. To demonstrate the impact of eddy current, we have done some other tests. On the left hand side, you will see the same result as we had in the first test. So untwisted wires are causing already a poor measurement result of 10% error, more than 10% error. But this will get a lot worse if we bring a metal plate in the near to the test wires. So you can see that the accuracy of the measurement is dropping, and there is a measurement error of 45%, and that's only related to the effect of eddy current. So you can see that the impact of eddy current can be very, very high. So to solve this issue, we once again are going to twist the wires. So on the left hand side, we twist the wires for the source, and on the right hand side, we twist the wires for the sense of the measurement. And as you can see, after we have done this, the accuracy of the measurement is quite good, regardless if there are many or metal plates in the vicinity or not. And that proves that also twisting the wires is solving the problem. Another cause of a problem might be that you are using multiple instruments at the same location in the production line. It is possible that the test current resulting of one instrument can influence the measurement of another instrument. Probably you have already figured out that also in this case the solution is to twist the wires. You can see here in the situation where we have twisted the wires of both of the instruments, there is almost no error measured with the two measurement instruments. And that's showing that twisting the wires is solving a lot of issues that are related to electromagnetic induction in the production line. By now you may conclude that twisting the wires solves all electrical interference and eddy current issues, but there is more to tell. Besides our standard battery tester in the BT3560A series, we have the BT4560 battery impedance meter that is also often used in the production line to measure the internal resistance at 1 kHz and also the electrode and reaction resistance of the battery at around 1 Hz. As the BT4560 uses a 1.5 test current at its lowest range of 3 milliohm, it is important to eliminate the effect of electromagnetic induction and eddy current even more. Because of this, the BT4560 uses a 4-terminal pair wiring method. An important difference between the 4-wire and the 4-terminal pair method is the use of coaxial cable. What we are doing in this wiring principle is that we are sending the source signal first through the core of the coaxial cable, and then it will pass the battery and returns to the measuring instrument. And when it is returning to the measuring instrument, we send it through the shielding of the same coaxial cable. And then you can see here, both currents are compensating for the electromagnetic interference. Then we have a connection wire, a return cable that makes sure that the signal, the current is flowing also to the source high shielding of the coaxial cable, and therefore also on the source high side cancels out for electromagnetic interference. Also, we use on the send side coaxial cables, and that makes it even more robust against external interference from inverters or other equipment in the production line. So this method even eliminates the electromagnetic interference better than the 4-wire method, but there is also a disadvantage for this technology, and that is that because we are sending the source signal twice through basically the wiring, the length of the wiring is twice as long as we normally have with the 4-wire method. And therefore, when you use the BT4560 in your production line, it is even more important to make sure that the measuring instrument is closely located to the battery that you want to test. So, besides wiring, the way of probing of a battery can influence the accuracy and the reproducibility of the measurement result. Before we focus on the probing itself, I like to mention the relationship between the total resistance of the test circuit and the measurement error. The total connection resistance, as I mentioned before, consists of the wiring resistance and the probing resistance. And that's for all 4 of the connections that we have with a 4-wire measurement method. On the right-hand side, in this graph, it becomes obvious that the longer the wires are, and the longer the resistance, or the higher the resistance of the measuring circuit is, the poorer the measurement result will be. So the message basically is that you should always try to shorten your connection between the battery tester and the battery as much as possible. Further, this also shows that there is a limit to the resistance that the connection can have, because otherwise the measurement instrument is not able to generate the current that you want to have for the low resistance measurement. So if the circuit for the source is exceeding 4 ohms in this case, then it's not possible to do any measurements any longer. Let's move on to the probes. What kind of probe do you need to use to get correct measurement results? There is a wide range of probes on the market, but we always advise to use a single contact probe, like in this case a needle probe, and not a multi-contact probe like the Krone that we have shown here. And the reason for that is reproducibility of the measurement. Our engineers in Japan have done several tests with single contact probes like the L2002 and also the L2000, which is a multi-contact probe. And as you can see here, the L2002 with a single contact probe is the blue trace, and this blue trace shows a very good repeatability. It's almost as flat as the Netherlands. But if we look at the multi-contact probe, which is the green graph, then you can see it's almost, you almost recognize the Alps in this. So this is showing that multi-contact probes give you a very poor repeatability of your measurement, and you should avoid that in your production line. Positioning of the probe is another important factor that can influence the reproducibility of your measurement. To decide what the best thing is, you need to understand what the effect of the AC source current flowing through the battery has on the battery. And as you can see here, we have the connection of the source high, and then here the source low. The current, the AC current flowing through the battery is causing a potential gradient. Basically, you can say this is kind of a voltage which is flowing through the battery. So the AC voltage drop over the battery. And as you can see here, near the source high and near the source low connections, there is a steep fall or a steep rise in potential, so voltage. And that is something that you have to keep in mind in what I'm going to explain in the next slides. It's very often considered that the best results are achieved when the probes for the source and the send signals are positioned very closely together. Let's take a look if that really is the case. If you're going to do it like that, and the send and source probes are very near to each other, you are measuring at this very steep area of the potential gradient curve. And because of that, it will have a big impact if the probing is done at a slightly different position when you put the source and the send probe very near to each other. Meaning that the repeatability of your test will be not that high, because there's always some mechanical tolerance in your probing position. So a small change in your probing can result in a not so good reproducibility of your measurement. Yeah. If we increase the distance between the source and the sense, the voltage gradient, so the voltage of the battery, will be measured at a less steep part of the curve. And then in that situation, the positioning of the probe will have less influence on the measurement result, repeating or giving you a better reproducibility of your measurement. In the production line, reproducibility is often considered to be more important than absolute accuracy, because you want to be able to compare the test results from day 1 with the ones from day 3 or day 10, and therefore repeatability is much more important than absolute accuracy. Okay, then we go to the third influence, and that's whether or not to use a multiplexer for AC/IR measurement in the production line. It's up to you, and it depends on different things. Using a multiplexer will reduce the number of battery testers and therefore can reduce the initial investment. Further, the use of multiplexers increases the flexibility. If the number of batteries that you need to test is increasing, the only thing that you have to do is just add another multiplexer card in the mainframe, and you have more channels that you can measure with. On the other hand, using a multiplexer will result in a longer testing time than when you do all the battery measurements simultaneously in parallel. Also, the wiring between the multiplexer and the batteries is more complex, and performing zero adjustment of a system using a multiplexer is a lot more challenging than just doing zero adjustment on a direct connection between the battery tester and the probe. So depending on the circumstances, you have to decide if you want to use a multiplexer or not. But when you decide to use a multiplexer, there are a few things you need to consider. One advice: do not use a standard off-the-shelf multiplexer for AC/IR testing. We have seen that there are many influences like electromagnetic influence, the eddy current, that have an impact on the accuracy and the repeatability of the measurement. So a multiplexer must be designed to take all these kind of things in consideration. What does that mean? Well, basically it means that the layout of the print should be in a way that there is a separation between the sense and the source. So here you can see at the top side that the source circuitry is in its place, and at the bottom side you have the sense circuit, and the sense circuit should be as small as possible, because then it will be less affected by external magnetic fields. As for the source, it is important that the considerations like the current flowing, the test current flowing in opposite directions that we have seen earlier in the presentation, that they are in the circuitry of the multiplexer. And if you do this kind of things, then you can get a good and reliable measurement result. I will show that to you in the next slide. So here you can see some measurement results that we have done with a multiplexer in combination with the BT3562A battery tester. But first we need to have some reference information. And that's why we did a measurement of a resistor directly connected to the battery tester. And that's the straight blue line shown here. After that, we did a test with a multiplexer, and the multiplexer is using the SW1001 mainframe, as you can see here under, and the SW9001 input card. That input card can connect to 11 different channels, as you can see here at the bottom of the graph. And the first measurement that we did was to connect the resistor to each of these channels in the 9001 card, and that card was positioned in slot 12 of the multiplexer. And this is the green measurement results. And you can see here, once again, this is very flat, meaning that there is almost no difference in the measurement of the channels on the multiplexer card. The same test was performed, but then the multiplexer card was not in slot 12, but it was in slot 1 of the mainframe. Unfortunately, or fortunately, I cannot show you this graph because it's completely underneath the green one. Well, this shows to you that there is no, it's not going to give any influence if the multiplexer card is in whatever slot of the mainframe also. And that's also very important because you want to be able to compare the measurement results. Our engineers in Japan also did a test with a multiplexer which was not suited for AC/IR measurements, and that's the blue trace. You can see the green trace once again is as flat as the Netherlands, but the blue trace is showing also hills and mountains like the Alps. And therefore, you can consider that the repeatability with a off-the-shelf multiplexer will not give you the good results. You need to use a multiplexer that really is designed for AC/IR measurements. Okay. Then we have basically covered all the important influences that can happen on the production line, and then we move on to guidelines for troubleshooting. There are many factors that can cause a degradation of the measurement accuracy in the production line, like temperature fluctuations, humidity changes, electromagnetic interference, etc. It can be a struggle to identify the cause of the problem with so many variables. That is why we advise you to go step by step. Change only one possible cause, like for instance the routing of the measurement wires, and check if this results in improvement of your measurement results. If this doesn't fix the issue, then change one other thing, like for instance remove metal plates which are near to the wiring, or change the pins to probe the battery. But do it always step by step. And doing in this order, you will identify what is causing your problem. We have made some example, and that's what I'm going to share with you on the next slide. In this example, we're going to measure a battery with an internal resistance of 1 milliohm. But the repeatability of the measurement is quite poor, as you can see here. So something is wrong, but what is the reason? Why is the measurement not giving you good results? To find that out, we're going to do basically two different tests. The first test will be to probe the battery and to do 10 measurements without disconnecting the battery. So keep the battery connected and do then 10 measurements. After that, we will do a test 2. And with this test 2, we will disconnect the battery from the battery tester between each of the measurements. If the results of test 1 are giving you a much better repeatability, it's already giving you an indication that something might be wrong with the probes. However, you have to confirm that, and that's what you did with measuring test 2. And then if this is giving you the result as shown here, where there is a lot fluctuation on the measurement, then you are 100% certain that this is caused by the probing of your device or your battery. The reason for this might be that your probes are being or have aged and need to be replaced, but it could also be that one of the pins has some issues and is not giving the right pressure on the battery and therefore has a different contact resistance. But it could also be that your battery is not fixed firmly in your production line and therefore can slightly move. And when that happens, it will probe at a different position, and then you can also get a poor repeatability of your measurement. So by doing this kind of test, step by step, you find out what might be the cause of your problem. All right, well, we have covered everything, and now we're going to look at the summary of the webinar, and let's go into it. Looking at the connections, correct wiring. The general advice is always to keep the wiring between your battery tester and the battery as short as possible. Always twist the source wires and twist them as long as possible. So also near to the battery, you should twist them as long as it is physically possible. The same goes for the source or the sense wires. Also, they need to be twisted and also near to the battery. Try to twist them as near to the battery as possible. Keep the wires as far as possible away from metal parts and plates to avoid the effect of eddy current. When you decide to use a multiplexer in the production line, only use a multiplexer that is designed for ACIR measurement. Keep the wires between the multiplexer and the batteries as short as possible. And the same thing as with a direct connection, always twist the wires, the source high and the source low, and the sense high and sense low. For troubleshooting, when you're evaluating and when you are going to do troubleshooting, always look one by one and in that way determine what the cause of your problem might be. And for probing, always use single contact probes. This will give you a much better repeatability of your measurement. And further, when you have a probing station, so probing fixture, always try to avoid use metal parts in this fixture, because the metal parts can be a source of eddy current as well. And in general, we advise to consider already at the beginning of the design of a production line where you are going to position your test equipment. And in general, it should be very near to the station where you want to measure the batteries. And check the background information in our instruction manuals. In all the battery tester instruction manuals, we have an appendix, and in this appendix, a lot of the information that we cover in this webinar is explained and therefore can be very helpful in finding solution to your problems. Okay, then we have finished the presentation and we have arrived at the Q&A session. You have to switch on your mic, Oliver.
Thank you very much. Thanks a lot, Roy. Thanks a lot. It's now time to take a sip of water. And also I would like to welcome Jutta from the product management team to join us when we want to answer some questions. So we have some questions already in the chat, so I will start right away to pick them up for you guys, starting with question number 1. Is it impossible to compare the ACIR and the DCIR values? If not, what should be taken into consideration to understand the incompatibility of both tests, as we are measuring the same internal resistors?
Yeah. Well, the principle of the measurement is completely different. Of course, one is using an AC signal and the other one is using a DC signal. The DC signal is basically a charge-discharge measurement and will give you a value. And as I mentioned in the presentation already, I think it's less important to have an absolute value of your internal resistance. It's more important that you can compare results to each other. So if there is DCIR measurement, you will get a specific result. It is important to find out if this DCIR measurement gives you a good repeatability. And then you can compare it with an ACIR measurement, but it is very difficult to compare them directly. Jutta, do you have anything to add to that?
No. So the ACIR and the DCIR is completely different measurement method. So it is difficult to comparing with the result. So most of customers evaluate by themselves. So to check with the DCIR result and the ACIR result, and to collect many of the data, and then they decided, okay, there's some correlation or not. So, yeah.
All right. Next one, I will go for the complex one first. What's the impact or influence of the distance between the current probe and the voltage probe on the measurement accuracy when touching the cell terminal? Can you answer that? Or?
Yes. Well, if you probe if the probes are very near to each other, what I explained in the presentation, it will have an impact on the repeatability of your measurement. So that will be less. The voltage difference that you measure will probably be higher, and therefore it could be that your internal resistance is also higher. But as I mentioned, I think that it's more important to have a good repeatability of the measurement than to have an absolute accuracy of the measurement. Jutta, you have anything to add?
No.
Okay.
Yeah.
Happy to hear that.
Yeah.
All right. Thanks for that. One or two questions I would like to summarize. It's basically about the cables altogether. One question is there a limitation on cable length? And the other question, or that I would like to maybe add to that, this is all about the cabling. What is the number of twists per meter in the cables? And maybe adding some other things from the last session we had about this, does it make a difference if we turn it clockwise or counterclockwise?
Jutta, can you answer those questions? Or?
Yes. So first, the limitation of the cable length. Our instructor manual mentioned for the recommendation cable. So basically, we recommend within 5 meters. But please keep in mind the shorter cable is the best solution to reduce this kind of influence. So we recommend to use within 5 meters, but 1 meter is also better than 5 meters. So,
yep.
And then
about the twisting. So, how is there a number of twists per meter, or does it matter counterwise, clockwise? How to do that?
The direction is not important things. The match number can reduce for the noise influence. So, but the number of the twist is depending on the cable types or situation. But please twist it as much as possible. So, and then you can get us some good repeatable measurement values.
Okay, so the finer the twist, the better it is, but it depends on the type of the cables at the end of the day.
Yes,
right?
yes, size or like length or yeah.
Okay. Then let's go to this question. Is it possible to do a reference measurement for ACIR with an ohmic resistor? Only ohmic components can be referenced. To be able to fully reference the measuring device, there would have to be a system with AC components, capacitance and inductance. Is this possible? Is that possible to answer?
Yeah. Well, what I can say is that our engineers advise to use a live battery also to do this kind of adjustment. Jutta, can you add a little bit more about this, because probably you're more the expert on this one than I am.
Sorry, can I repeat the questions? So
it's, if you open up the chat, it's at 10:44. So is it possible to do a reference measurement for ACIR? And to be able to fully reference the measuring device, there would have to be a system with AC components. If it's more complex, then we may want to put it in our written answer.
Yes. Well, in general, what we advise normally, I think, is that you have to do a reference measurement on the battery itself, but do that in a clean environment. So try to make an optimum as possible situation, and then do a reference measurement. And after that, you do a check when the instrument is and the batteries are installed in the production line. Is that correct?
Yes. So basically, the reference value should be made in like a R&D situation. There's no like power line or stable temperature, or so this is like a ideal situation for the measurement. And then this could be the reference value. And then you go to the like a production line or like an actual situation, and then you can compare with the like result. So, but probably it is better to summarize for this kind of information, and then to
I think so. Okay, good. There's two more questions I see right now. Number one, just before we go to the slide, is there a difference in measurement principle for OCV when measured in conjunction with ACIR or measuring OCV exclusively? Is there a difference in measurement principle for OCV?
Yeah, well, in ACIR we measure we measure only the AC voltage. So we don't measure the DC voltage, the DC component, which is generated by the battery itself. There is a capacitor in the circuit that isolates the DC voltage. So the measurement is different.
Okay. And then there's another question that refers to slide 33. The considerations taken in slide 33 are for the case of prismatic cell testing. Is that right? That's 43. Sorry, that's 43. We have 10 before.
Okay. 33. Sorry. Page up. 33. Yeah. Well, we showed this example because it's graphically easy to demonstrate the difference. But in general, it's also applicable for cylindrical cells. It's of course a little bit more different, but the principle is the same. So if there is any possibility to have the probes a little bit further apart, it will improve your repeatability as well. So for other types of battery, like the pouch or cylindrical cells, also this has an effect. It's not only for prismatic cells.
Okay. There's a question from Elias. Is there a specific level of current described by the standard that should be used for battery production testing? Since BT4560 uses a higher value of current, is this an advantage?
Well, the higher the current that you are using, the lower the resistance, the internal resistance that you can measure. And that's why for the very low current ranges, the currents are increasing. But that's basically the reason why we are using higher currents, but there is no, in the standard, there is no indication what kind of current you need to use to measure the internal resistance of batteries.
Okay. All right, then there's two more questions we have here, referring to the twisting of the cables here. In addition, are the HIOKI measurement leads, for example, 9453, already twisted? It's one question. The measurement leads?
It's already twisted.
Okay. Quick answer. Very good. And then you're referring, as we refer to twisting the wires, should shielded wires also be twisted? And do you recommend shielded wires?
So basically the twist, if the customer use for the shielded wire, the wires should be the twisted, because the shielded can reduce for the electrical noise, but the twisted pair can reduce the magnetic noise which generated by current. So the shielded and the twisted can reduce different kind of like a noise. So if you use for the shielded, of course the shielded cable it can reduce for the electrical noise. It is better to use for the shielded cable, but also you should twist it as much as possible, and then you can get the more repeatability values.
All right, thank you very much. I think that was pretty specific. And one more question we have popping up now. Is there relevance for the frequency of the AC? In which frequency do we need to measure?
Well, that's a little bit depending on the battery that you want to test. We see a trend to higher capacity batteries. And when you're going to test higher capacity batteries, then normally it will be a lower frequency that you're going to use for the test. So we see that customers that are having this high capacity batteries are testing the batteries in the production line, not at 1 kilohertz, but at lower frequencies, around 200 or 300 hertz, instead of the 1 kilohertz. Because but now it becomes very technical. They want to know basically the crossing point where there is no impedance in the battery. And for larger capacity batteries, that's at a lower frequency than the 1 kilohertz. So traditionally it's the 1 kilohertz because it's near to the zero impedance crossing. But with the new trend and bigger capacity batteries, there is a trend that you have to measure at lower frequencies to arrive at that point. But we will summarize and explain that and send you some more information about that.
All right. Thank you very much, Roy. Thanks a lot. Thanks also for all these questions. The follow-up, the meaning is to eliminate as possible the reactive components. That would be the meaning. Okay, so probably it would make sense, as it's a bit more complex, to write this down a bit, to summarize it and then share it with you after the webinar. We also had a lot of questions, a lot of interest. I see almost everybody is still here for the Q&A, so the interest is very high. Thanks a lot for joining. Thanks a lot for your interest. Really, for the full hour almost now that we are completing, where we can go to the end of the slide deck, Roy. So
yeah,
as announced in the beginning, we will share the recording of this webinar with you. We will also share the a PDF version of our presentation, of our slides, and of course also the contact information for the technical team and for HIOKI in general, and also to find the right support in your country where you are. With this, I would like to close this webinar. Again, thank you very much, Roy, for the presentation. Thanks, Jutta, for supporting with the question, and everybody for joining the webinar, for your interest in HIOKI products and HIOKI solutions that we could hopefully help you with to improve your measurements for your production and for your applications. thank you very much and hope to see you soon again.
Thank you. Bye-bye.
Thank you.
Goodbye.